and then start. Here we go.
Hey, good morning, everyone. Welcome to our another webinar, and today's topic is going to be STEAM in practice. It's going to be presented by Spirax Circle. We thank you all for joining us, and as usual, today's session will be presented by Nick Wisby. Yeah, and as you may know him, Nick is a dedicated and results technical sales support engineer with a rich background in engineering industry with over 2 decades in experience in technical applications, electrical engineering, control and instrumentation, and also STEAM. So he's been part of Spirax Circle for 7 years now, and he's currently based in our Spirax Circle office in Nairobi, Kenya. So today we will, of course, cover the STEAM practice, and as we all know that we endeavor to have a mechanically correct system, which can play a big part in reaching process as well as sustainability objectives, and as well as reducing the maintenance cost of your systems wherever you are. So this session will be a total of 90 minutes with 60 minutes presentation, and later on a 30-minute Q&A session. So of course we'll have your microphones will be muted throughout the session so that you cannot be able to hear the presenter, and you can be able to submit your questions through the Q&A function, which can be found on the webinar's dashboard. Yeah. So the questions will only be seen by the hosts, and it may not be possible to answer all the questions during our maybe 30 Q&A session. But we will reach out to everybody after the session to ensure all the questions are answered. So if you don't see your question answered at this point, we will ensure that we cover all the questions. And what we're saying is please complete the feedback form after the webinar, and with that we'll be able to send you at least attendance certificates, and also be able to make any follow-up that you may have with us. Yeah. So for the questions, the tab you only you can just type your questions in the compose box and then click select send. And if you maybe don't want to have your name shown, you just click on the anonymous, and then before you send it, and then you click send, and we'll be able to see the question on our side, and we will be able to publish so that everyone can be able to see your question. You could be having similar questions, but that is the reason why we'll be able to publish. Yeah. Okay, so can go next. So I may hand over you to Nick so that he can be able to proceed on with the webinar, and I hope you do enjoy the webinar. Thank you.
Thank you very much, Anthony. So welcome everyone, and thank you for joining us. So the course will cover the following subjects. We'll cover monitoring distribution losses, control recover of flash steam, condensate losses, reduce blowdown losses, eliminate standing losses, and meter usage. So the course is designed to be a basic knowledge, but we do offer in-depth training on request. So if you feel there's any questions you want to submit, please feel free. We love questions during these sessions. Equally, we can follow up with you as well, as Anthony said. So first off, who is Spirax Circle? Again, I know I start the webinars with this. It's just for the new joiners, so to show the presence we have. Initially, we were started in 1888 by Sanders and Readers under the name Sanders and Readers Co., which was later formed the Sarco of our name. In 1932, we started manufacturing in the UK, and we branded the product range under the name Spirax. So this then became Spirax Sarco. We have 145 operating companies, 180 plus local sales offices, and 55 countries are served by distributors. So the figures are a little bit low on here now. We have over 10,000 employees, and I think it's about 2,500 local service engineers. 29 manufacturing sites on 4 continents, and our global HQ is in Cheltenham, which is in the United Kingdom, the southwest of the United Kingdom, and of which we have 59 customer training sites. So we have many companies under the Spirax-Sarco Engineering PLC, which is now changed to Spirax-Sarco Group. The thermal energy management is handled by Spirax-Sarco, Gestra, and Cotopaxi. Electronic thermal solutions, so things that are electronic and such as heat tracing, those kind of things, Chromlux and Thermalux. Watson Marlow is also under our group. They deal a lot with peristaltic pumps and sort of small flows. And again, we're a FTSE 100 company, turnover about 1.4 billion pounds per year, and over 30,000 products in our range. So main product areas, we offer boiler house controls, clean steam, humidification, isolation, and many others. Services, we have 24-hour response, health and safety compliance, steam quality testing, and valve reconditioning. And we are experts. This is the boiler that we actually use in our headquarters for a training. So when you attend training in the UK, we walk you around this boiler. We get you to do the controls on it. So we do this day in, day out. We know our boilers and our equipment. So back into the course itself. So typical losses on a on a steam system. So if you've got a fuel input of 100%, as it shows here from your boiler, you'll expect to lose 20% just through your flue gas on heat, of which you'll also then see blowdown losses of 2% and radiation losses of 3%, giving you a heat output of 75% of what you've actually produced in your boiler by the time it hits distribution. Distribution losses, you'll then see 5%, flash losses another 5%, and condensate losses another 10%. So the actual heat that you get to your process is around 55% of what you first produced at the boiler. So wet steam, why is this heat important? So wet steam is what we're trying to fight. We want a dry steam so that we can have as much heat, as much energy as possible when we reach our processes. So wet steam is a mixture of dry saturated steam, which is what we want, and water droplets, which has been carried in the system. It does not contain as much heat as dry steam, so the energy that it can offer, it can give up, the enthalpy is lower, and the water acts as a barrier to heat flow. Compared to the figure given on for your pressure on your boiler, you will be able to notice using the steam tables that the enthalpy of evaporation is much less than for wet steam. Or if your enthalpy of evaporation is much less than shown in the figures, then your steam has wet steam. So pressure and temperature relationship. So unlike medium temperature hot water or oil systems, we control steam by manipulating the pressure. So when we change the pressure, we change the temperature. For instance, 1 bar G would have a steam temperature of 120 degrees, and it has a specific enthalpy, or HF, of 2,706 kilojoules per kilogram. So this information, together with the enthalpy of both steam and water, can be found in the steam tables, and this allows us to work out how much energy, how much temperature we need at the end of our line. On the table in front of you, water exists below the line, and steam is above, or on and above the line. Superheated steam would be the higher you get above the line. So again, the pressure temperature relationship also allows us to tell the volume of the steam. So this is important when it comes to distribution. Costs of pipeworks, equipment, the larger they are, the more expensive they are. So most boilers will run between sort of 7 bar and 10, maybe 11 bar. Because here, as you can see, the specific volume of the steam is much smaller than it is up here. So it allows you to make smaller pipework, smaller equipment. Then you can adjust the pipework to suit when you are close to process. So it's one of the ways we can reduce the costs. So for instance, 10 bar steam has a volume of 0.177 meters cubed per kilogram, whereas 1 bar G has a volume of 0.881 meters cubed per kilogram. So it's almost 5 times bigger at 1 bar as it is to 10 bar. And that would then give you choke flow, give you struggles to reach temperature if the pipework isn't sized correctly. So flash steam losses. Why are they important to us? So steam condenses on energy and releases the energy. Condensate can exist in at steam temperature, so you can have both condensate and steam at the temperature where you can have both. So the Hg, total heat of the water at 10 bar, is 2,801 kilojoules per kilogram. So it's higher at 0 bar, which is 2,676 kilojoules per kilogram. What does that? So what does that mean? Effectively, it's the energy it can give up. Well, that's why we increase pressure. So condensate reverts back to steam with up to 16% of condensate flashing, becoming flash steam. Does anybody have any questions at this point? Anthony, is there anything on the board?
No questions for the time. Thank you.
Okay. So how do we reduce steam? So there's many products out there. Being Spirex, we talk about the ones that we know. So for instance, thermostatic reduces condensate temperature by 5 degrees before it will release from the trap. And that means that we can reduce the flash steam you see in your system. So on our particular traps and many other thermostatic traps, they are compact design. They tend to be modular, so quick installation, and they have limited leak paths because of their design. There's zero potential for incorrect assembly as well. So this particular unit is what we call our STS 17.2. So it's a modular design. It allows for inline servicing. All parts are 316 stainless steel, and the ease of design and specification. So that means it's designed to be user friendly. So solution 2, we want to recover that flash steam. So if we can't remove it, we want to recover it. So many systems out there to do it. We call them the FREM system, so the flash recovery equipment unit, effectively. So it can recover steam, flash steam from and from energy from the boiler. As a rule of thumb, sort of 14% of condensate will flash off when it reaches somewhere close to atmospheric pressure. In traditional steam systems, it may be vented off as it's been looked upon as too costly or too much trouble to make use of. Many of you will have pipes that you can see from exiting a building or exiting a roof where you can see steam coming off. That's normally where you need to equalize the pressure to atmospheric. We can recover the steam there. You can recover the steam from there using flash recovery vessels. The challenge is that it can only be recovered under pressure. So this has to be done in such a way that the temperature does not cause cavitation in the pumps. That's why we have to vent to atmosphere. But then we can recapture that way by using one of these units. Do we have any questions at the moment?
So far, so good. We can proceed.
Okay. So STAPs, other applications are available. So another way we can monitor our steam traps, make sure that they don't fail, we're not losing steam, we're not losing flash, is by putting our STAP system on there, or an instrument on your traps. It allows you to monitor those remotely, and tells you instant you have a failure. So as soon as you have a failed trap, particularly if it fails open, you are losing steam. So I did a calculation for a customer in Ethiopia last week. We worked out that from the steam traps that they had failed, they were losing around $56,000 a year just from leaking steam traps. So that's why we need to make sure everything is in good working order, that we see the traps failing almost as soon as they do, so that we can then repair them and keep costs as low as possible. So our particular units have 3 components. So you have the head unit, which is the transmitter, this area in black. Then you have the receiver, which is this version here, and then the software. So these 3 components can allow you to monitor remotely your trap stations. So what is condensate? So condensate effectively is heat energy. Yeah, so what we have is we have the enthalpy of evaporation, latent heat. Then you have the enthalpy of water, which is sensible heat. Combined gives you the total steam value. So in condensate, we have water, we have chemicals, and we have effluent. So we need to be able to separate those the best we can, but also recover the heat, because you've paid to heat that. You don't want to waste it. So 85% of condensate. So we work on what we call the 85-85 principle. So if you are recovering 85% of your condensate, your whole tank, so your feed tank to your boiler, will be around 85 degrees. So in an ideal world, we would recover 100% of condensate from the process, such as vessels, calorifiers and jacketed vessels. However, some processes, this is not possible due to either contamination, or the steam is being consumed by the process, such as humidification or injection, or it's contaminated, like I just said, so unfit for the return back to the boiler, or for the feed tank to the boiler. So every increase in of 6 degrees, increase in feed water is 1% fuel saving. So this is why it's important to heat your tanks properly. So we can calculate the current condensate recovery. So if you take your raw water parts per million minus your feed water parts per million, divide that by raw water parts per million and condensate parts per million. So the EG, the formula there, it will give you a particular figure. So in this case, we've used the 200 minus 50 divided by 200 minus 10, gives you a 79% return. So it's a very easy formula for you to be able to calculate the amount you are returning, and then from that temperature that you have in that feed tank, you can also, by increasing it a degree, as we said before, you can see the savings in fuel. Do we have any questions at this point?
Yes, we do. And I'll start with the first question. So the first question is, by flash steam, do you mean the condensate that comes from the traps on the main steam line, that is 7 to 10 bar?
So when we say flash steam, what we're talking about is you have traps which remove the condensate, as the question says. That will be under pressure. You have a differential pressure that then comes across the steam trap. So when it reaches the condensate line after the steam trap, you will have a percentage of steam which has turned from where the water has suddenly decompressed. The extra void, the extra space has allowed it to flash into steam. So all condensate pipes, unless they're very, very close to atmosphere, from the differential pressure, will contain flash steam. So there will be a certain percentage of flash steam in even your condensate pipes. Hopefully that answers that question. Is there any else?
Yes, there's another question. So the second question is, should a frame vessel be insulated or remain uninsulated to radiate off the heat to encourage the flushing in the vessel?
Good question. So anything that contains steam, you don't want it to lose the heat. So I would suggest it has to be insulated. We would insulate our MFP, for instance, and that's a condensate, because for that very reason, we're trying to maintain as much heat as possible. So a frame unit is no different.
Okay.
So when I say frame, I mean flash, flash vessel.
Okay. So for the third question is, can you please explain about the flash steam recovery? Where can they be installed on the line and when should they be used?
So I'll flash to the next slide only because it gives me a good example to show you. So for instance, this would be a typical way to be able to recover flash steam. Many of you will have a pump trap of some sorts, be it Spirex or others, to allow you to pump back the condensate from your line. So you'll have a receiver tank. We as an industry, we have a vent to atmosphere so that we can allow this to not be under pressure, so that we can avoid the PED regulations, but also to flash off any extra energy, giving you the hot condensate alone at atmospheric pressure to be able to pump back. Now this vent will go for a wall or it will go for a roof space, and you'll see steam whispering out of the top of it. That's what we call flash. We can recover that flash because it's still energy, it's still steam, be it at a low pressure, and we can use it elsewhere in your process. So perfect example for flash steam would be running, say, a small heat exchanger for hot water in a bathroom or a washroom. You could use it for washdown stations where you need some hot water to clean. Many other applications where we can recover that. You can even re-energize it using motive steam, so you can bring the pressure up and then you can use it back into process. So hopefully that answers that question.
Thank you. So we have one last question. Is coming from Plum. So how could I calculate the condensate recovery using my steam flow meter? Will it be a more accurate value than the percentage ppm calculation?
So if you're talking about for trap sizing, there's not really a need for calculation on those. The idea is that when a system is cold, we believe or we treat it as if 100% of the steam is being turned into condensate. This is before warm up. So when you size steam traps, things like that, you would size them for double the load. So if you have a running load of 500 kilograms, we would say size the trap for 1,000 kilograms, because that allows for ample space for runoff when draining the system to try and get it warm quicker. I'm hoping that answers that question. When it comes to flash, I mean, you can do the differential pressure calculations and be able to work out the percentage of flash that you're going to get. If you contact us directly, myself or one of my colleagues, we can go through those formulas in detail for you to be able to help you with them. They sometimes they're easy to do once you know, but the explanation of them can be a little bit tougher.
I believe also what he was asking in terms of condensate recovery rate. How can he calculate using the steam flow meter instead of the parts per million calculation, the percentage that you have shown? So is it basically, how does he calculate using a steam flow meter, and will it be more accurate than the initial formula that you have shown?
Yeah, so you can use your flow meter. Again, like I said at the beginning, you're going to have almost 100% return because it's all cold. But it will depend on your process. So you will see losses. The reason why I'm struggling with the question is, as a rough rule, we would use 25% losses. But There is other processes that will lose more. There is other processes that will return more. So it's I'm trying to think of the best way to calculate it.
I do believe.
Yeah, sorry, go on.
Yeah, I do believe in terms of flow meter, if he has a steam flow meter, can he take advantage of that flow meter to do a calculation of the condensate recovery rate in his system? But I do believe in that case, he also needs to have condensate flow meters also, so that he can be able to see what goes back.
Yeah, for true losses, you'd also need one probably on your blowdown, your TDS, wherever that retains, because then you're seeing what you're producing, what you're having to dump, and what's returning. So effectively, you could work out the value for money and the figures of percentage of return via that way. But yeah, you would need a meter on both sides.
Yeah.
Not to forget the feed water itself as well. So the raw water that you're bringing in. Because that again is a calculation cost. You've had to replace water in the boiler.
So I do believe he needs a steam flow meter, condensate flow meter, and also the makeup flow meter, so they can see the difference, or at least the steam flow meter and the condensate return flow meter.
Yeah, it depends the accuracy level you'd want. The very basic would be the steam out, the condensate in. But then if you really want to be truly accurate, you would then add to the services. So such as you could add to the makeup water, you could add to the fuel that the boiler's using, so you can see how much bang for your buck you're getting, which would give you the efficiency of the boiler. And then any losses, any dump to drain that you're doing. So it depends which level you talk about. And minimal, you would need 2 meters. Any other questions?
Yes. The other question is the condensate recovery. Can we calculate using the condensate recovered volume and the steam generated volume? Any variance to the ppm approach?
Yeah, you could. I mean, you get the value of effectively how efficient your system is by seeing how much volume of condensate you've sent back via how much steam you've produced. So again, it goes back to the meter question, really. The most accurate way is going to be via meters. There's always a way to calculate it, but it's going to be rough unless you have a working figure, which is calculated by the meter itself.
Yes. Thank you. Also, noting from the question from Rama is that just a clarification is, yes, you can use a condensate recovered volume and the steam generated. If it's for steam generated, do not use the volume, but use the kgs, because the volume changes with the pressure. So just
exactly,
just a point to remember. So that is a question that is hard from Heineken. That's Bloom's since asked. That's why he's asking in terms of the flow meters. Yeah, it's a question that is hard from Heineken. Hence why he's asking it. Yeah. There's another question from Murray. This is for steam mains distribution. Is mild steel brackets black pipe best, or is stainless steel pipe better? I assume stainless is a bigger capex investment, but will require less maintenance as less corrosion.
So yeah, I mean, you've said quite a bit of the answer that I would give you there as well. So if you talk purely by material, not cost, stainless steel is always going to be the better material. It's harder, it wears less, it's not prone to corrosion, as you said, so you won't see the rust. But it is expensive. So a way to lower costs, if stainless steel piping is something you would like, is by increasing the pressure, because then you lower the volume. Mild steel though, I mean, mild steel has been the standard for steam systems for many years. There is, although it does wear, it depends on what process you've got. So if you've got a steam as an energy for, say, heating vessels, which is not going to come into contact with any of your product, mild steel is fine. I mean, you will have more maintenance costs compared to stainless steel, but it's a lot cheaper. If you've got a process where it needs to be clean because you have direct contact of steam with product, so we would say that steam is then an ingredient. So for instance, if you're I'm trying to think any foods, noodles, I think they sometimes get steam injected directly to them. Cornflakes as well, Weetabix, those kind of things. You're actually using steam as part of your product, so the steam would need to be as clean as possible. But again, there is ways around that. As long as you can purify the steam close to point of use and then use stainless steel piping afterwards, it doesn't mean your entire system needs to be stainless steel. You can reduce costs by the mains and the distribution to a point being mild steel and then changing to a harder material. But just from the point of view of maintenance and the erosion, corrosion, as you said, stainless steel will always be the superior material. Hopefully that answers that question.
Thank you. We have another question from Rama. And the question is, we collect our condensate from the process in a common reservoir. The challenge we have now is how to recover the flash steam from the reservoir. Please elaborate how to deal with this.
Yeah, so if I go back to the FREM units I was talking about, so for instance, the vapor recovery, flash recovery. So we could take the pipe that's coming from I imagine it's a condensate recovery unit. So you have an open to atmosphere pipe. That pipe would then go through a recovery unit like this or very similar. Doesn't always have to be as complicated as this. You could either, as I was saying, you could re-energize the steam by adding a motive steam connection. Something, say the steam is coming off at 0.5 bar, but usable pressure is at 5 bar. You could use motive steam, speed it up. You could also use the steam you have. I mean, you still have temperature there for washdown units. It's as simple as connecting to the venting pipe on your CRU. You need to be careful you don't pressurize the vessel itself when you're connecting things to the pipes. But if it's something you want to explore or you want to learn more about, please feel free to contact one of us. We have many different solutions. There's many companies that also offer solutions, so we can speak about the theory or the product themselves when at a time that's more convenient to you. Hopefully that answered that one. Any other questions?
Yes, I do believe it has answered. Also, there's also a similar or easier, rather than a frame, you can also put an exhaust vapor condenser. Yeah, I do believe also that can be used as on top of the reservoir or the condensate recovery unit.
Yeah, so FREM as a term in Spirex, it just means flash recovery equipment. So we cover a whole branch of different products that we can offer in that range. So it doesn't always have to look like the skid system that I show on these slides. It can be individual pieces of equipment.
Okay. Right, thank you. There's a last question also.
Yeah, keep them coming. I'm really enjoying these. So.
Yeah. So please clarify, is feed water the makeup water from the softeners or the water in the feed water tank, which is in bracket makeup water plus condensate? So
feed water would be makeup water plus condensate. So it tends to be the feed to your boiler. So the feed tank is called a feed tank because it's feeding there. Some systems directly add water to their feed tanks plus the condensate. Other systems have a separate tank which then feeds into that one. So it very much depends on your system, but for the conversation with Spirex, when we say feed water, we mean feed to the boiler.
Okay, thank you. Thank you for answering the question.
No
We have no
problem.
more questions, so I believe we can proceed, but keep them coming and we will be able to answer.
Yeah, again, we very much enjoy your questions. So the more questions, the more engagement we get, the more we enjoy it. So please feel free to ask as many as you need to. So again, I know you've already just roughly seen this slide, but this would be our mechanical CRU. So CRU standing for condensate recovery unit. So in some of the as a sum of the cost of raw water, the cost of chemicals to treat the water to get it to a condition that we can use it in our boilers is expensive. So when we return condensate, we are effectively saving on the chemicals we need to use to treat water. So that's why we try to return as much condensate as possible to reduce costs. It's not always possible to return the condensate to the boiler house under gravity. So when we have a pump trap, it's designed to give it a little bit more push so that we can return that back to the system. We can do that either mechanically, as shown in this picture, or we can do it electronically. The mechanical version, basically, it's a larger version of a ball float trap. So many of you would seen float traps on your system. We then add a motive steam connection. So when this ball reaches this point, in normal use, you've got the ball moving like this, like a float trap. It'd probably be the other way around, sorry, only because the flow is this direction. If for any reason this fails to pump anymore because the pressure is too low here, the ball will rise higher, and as it clicks, it opens the motive steam. So then you repressurize the condensate line with the motive steam pressure, which allows for the flow, and then it will drain the trap. So again, like I said, it's a mechanical flow trap with a motive steam connection. Any questions on that particular CRU unit?
So far, no questions.
Okay. So we go to the electrical versions. I think this may be similar to the question, the system that the gentleman was saying. So on this one, you have a large receiver tank, a vent. So this top section effectively is a lot bigger, is the same. But we have electrical pumps, which will be fired by a level sensor in here to push the condensate back down the line. So back pressure here is important. I've been to many sites where I've seen this U siphon a little bit too short. So this picture is a little bit misguiding, because the loop needs to be sufficient enough that you can keep a back pressure of water which is in there. This is meant only as a overflow. So you want to trap the steam inside here, vent the flash out of here. If you see steam in your system coming out this pipe, it can be one or two things. Either the water seal that's in here has been removed, so there's no longer a back pressure to stop that steam venting through the overflow, or if it continuously happens even after replacing the water seal, this pipe isn't long enough. So as a general rule, we would say that this comes down to about just above the floor, and then out, just to increase that back pressure. Again, like I said, the level sensor that's there, condensate flows in, fills the tank, reaches the level sensor, and then it either fires one or both pumps. Very simple system. Any questions on that one?
No questions?
No? Okay. So let's talk about the actual costs that we can do. So extra condensate recovery, so say it equals 8,000 kilograms an hour. Assume condensate at 90 degrees and replacing that water from cold makeup is at 10 degrees. So energy recovered would be 8,000 times 4.19, because that's the That's the kilojoules per kilogram, times 90 and minus 10, so that's the temperatures, equals 745 kilowatts. Sorry, divided by 360 equals 745 kilowatts of energy. So boiler efficiency, let's say it's at 80%. For the energy we generate is 745 kilowatts, equals 931 kilowatts from the efficiency. So plant operates 10 hours, 5 days a week, 48 weeks a year. So that's 2,400 hours. Coal energy cost, we use coal on this only because it's more global. And that's the kilowatt hours, dollars per kilowatt hour. So the annual saving would be 931 times by 2,400 for the hours, times by the costs. So that gives you $26,812 annually saved by just increasing the kilograms per hour that you're returning. Does anybody have any questions on that formula?
Not yet.
So if we talk about water and effluent, so water and sewage cost, let's say per meters cubed in this case is $1.19. Sorry for anybody who struggles with dollars, because of the people who are in this training, dollars is kind of universal. So we can share the information if you want to do local calculations as well. So in this case, water saved would be 8,000 kilograms or 8,000 liters times by 2,400 because that's the working hours, divided by 1,000, so that's 19,200 meters cubed saved. So the annual water saving, so we've said that it's $1.19 per meters cubed times by the meters cubed we've saved would give you a saving of $22,848. Combined coal, water and effluent savings, then if we add those both together, we get a value of $49,985 that can be saved just by returning that little bit extra condensate. So you got the plus to the cost of the chemicals, which can vary from site to site, and the increased blowdown that you would have from needing to return those, and the effluent cooling costs. So does anybody have any questions there? I guess the silence would be no, Anthony.
Just check.
Yeah.
Okay, no, that's maybe a comment. Yeah, there's no question. Just a good elaboration of the electrical condensate system and the drawing on the back pressure concept in the overflow, on the touching maybe of the back pressure concept in the overflow.
Yeah,
it's just a comment.
Yeah.
So yeah.
Thank you. So what is blowdown? So why do we blow down our boilers? So there's different water sources and water authorities, which will give you a different ppm, so parts per million that you will need to blow down. So different water treatment requirements, oxygen scavenging chemicals may also be required, differing ppm values from boiler feed water. So what the boiler requires a blowdown point. And boiler water ppm increases concentrates. So in the boiler, the longer you run it, the more you return, the higher the concentration of ppm. So we need to get rid of that. And the reduced by dilution of lower ppm feed water. So by the feed water we return, especially when you add makeup water and whatever else, you can lower the parts per million by replacing the water in the boiler. So blowdown types, so build-up of salts, which is your TDS, so total dissolved solids in water. Feed water, so you have the impurities, again, which is salts that you see, chemicals and solids that you've got from your return tank or your feed tank. Build up a sludge at the bottom, which is a mixture of the captured elements from your chemicals, but also general wear and tear on your system. It could be erosion, corrosion that's been washed back from your condensate system. And you want pure steam out, or as pure as possible, because you don't want to re-pollute your steam system. So we would try and blow down the salts or TDS via the blowdown on the side, and bottom blowdown, which will remove the sludge and anything that's fallen to the bottom. So I don't know if how aware you guys are. So how a boiler goes critical is usually because of bad TDS, bad water quality, and bad blowdown. What you find is you get a crustation on the fire tube, so that a scale actually has a higher melting temperature than the steel the boiler is made out of, but it also reflects heat back into the tube rather than allowing it to be inducted into the water around it. As the scale builds, the heat that's reflected back in builds, and at some point, if this boiler hasn't been maintained, it hasn't been watched, the fire tube will collapse, which then lets all this water at pressure go into the fire tube, but you now have an open space. So where you have an open space, you then suddenly have flash, the expansion of this water into steam, and it creates a rocket effect with this fire tube. Boilers quite often, when they go critical, when they implode, will travel several thousands of meters. I remember one thing, one that I was shown, it went through the boiler house, across a road, taking out a couple of cars, through a smoking section, shelter, and then ended up in a factory, which was, I think, about half a kilometer, maybe a bit further. There was a case recently, I believe, in Tanzania, where where a boiler went critical, and sadly killed people. So it's very, very important, the maintenance that you do on your boilers, the checks that you do, removing TDS, doing the blowdowns, which we will cover in next month's webinar, where we cover solely boilers. So why reduce blowdown? Boiler PPM dictated by boiler manufacturer. So there will be a parts per million that is stated by your on the plate or in the instructions of the manufacturer, which will say which point that you want to blow down. I think ours is 3,500 as a standard rule that we use, but if it's higher or lower by a little bit, it's going to be around there anyway. So as soon as you reach that 3,500 or thereabouts, depending on what's stated, you should be blowing down. So it can be as high as 25% to 30% of the boiler volume in areas of poor water chemistry. So if you're not looking after your water, the percentage of contaminant effectively you can find can be quite high. So by returning the condensate, we can reduce the amount of raw replacement water required, reduce the amount of cooling water required. We can, the challenge you have when cold water enters a boiler, you get what's called thermal shock, whereas a slight moment, depending on how much you've put in, where your boiler is no longer producing steam, because it now needs to heat that water required to the pressure required to be able to reproduce. So if you get a system where you see many starvations to your process, potentially it could be because you're getting thermal shock to your boiler. There is other reasons as well, but that can be one of them. So it reduces the amount of replacement chemicals required. If you return condensate, which is already treated, you don't need to treat raw water, so therefore you reduce the costs there. And it maintains a stable steam production output. So, well, again, where I was saying, because of thermal shock, if you have no thermal shock, because your condensate is returning and you're having a high temperature into your boiler, it will take less time to produce steam. So you'll get over the same period of time, a higher steam output. And it reduces the amount of hot water going to drain. So if we can limit the blowdown, we can save energy by not wasting all that hot water. So does anybody have any questions at that point?
No questions yet.
Okay. So the formula. So an example of this is for 10,000 kilograms an hour on the boiler. So the maximum allowable TDS on this is 2,500. and the boiler feed water TDS is 250 parts per million. So we can calculate the blowdown rate by 250 times 10,000 divided by 2,500 minus 250, and that gives you 1,111 kilograms an hour. So that's how much you will need to blow down from your boiler. So effluent to drain, as we just said, is 1.1, so 1.1 tons, let's say. Cooling water, enough to reduce the temperature to 43 degrees C. So the raw makeup water is the wastage plus the cooling water replacement. Replacement chemicals are determined by location and process on your costs. And the heat energy to waste, so it's going to be the 1.1 times by the boiler pressure, which will give you your enthalpy. So the example applies to a zero condensate return system. So when the parts per million of percentage of condensate return known as appropriate calculations are applied. So it's kind of our get out jail clause there, but effectively, and a zero return on 10,000 kilograms an hour. This is the formula you can use to see how much your blowdown rate should be. So savings by blowdown reduction. So a quick formula here. So it shows the bar pressure, PSI for anybody who works in it, and the fuel saving for each 1% of blowdown that you save. So effectively 10 bar boiler will save you 0.21% of fuel if you can limit your blowdown. And here again, it's set on a 10 bar boiler with blowdown reduced by 50%. So equals a 9.5% fuel saving. So blowdown losses solution, how can we recover some of that? So we have automatic timers. So rather than relying on a boiler house man to limit the amount of time he's blowing down, you can set a timer which will give you a flow rate because of the orifice on this, which will automatically do it. Automatically TDS blowdown as well. So when it reaches rather than having to have a cycle where you say you blow it down once a day, twice a day, if you are actually monitoring via conductivity, the TDS, and then this will blow down automatically when it reaches it. So in theory, if your blowdown is too much, by having the conductivity, you will limit the amount of blowdown you're doing, so therefore make savings. And automatic boiler capacitance level probes, so level probes to tell you where the level is running back to a pump, so you have modulating control into your pump. So I would say these are probably connected. Modulating control means for the Kenyans in the room, poly on the boiler water, slowly. If you have on-off control, you tend to work in what we call a window. So you have a high level and a low level. The boiler doesn't fire until it reaches the low level. It doesn't turn off until it reaches the high level, which means it's added a large amount of water. When you've got modulating control, because you're maintaining a particular level, which normally is plus or minus 1%, depending on the manufacturer of the probes, you add less water. So yes, you use more energy on your pump, but you use less energy heating the water in your boiler to steam. So as the larger volume being the water in the boiler, I would suggest that the modulating saves more money, even though you're running the pump, because of the amount of volume you're heating. Anybody have any questions there?
Not yet.
Okay. So blowdown losses, solution 2. So typical boiler feed water, if we say it's at 250 parts per million. Reverse osmosis level, 5 or 6 parts per million. So you can see the savings you can get there. So by using reverse osmosis to soften the water, lower the parts per million, which would reduce the amount of blowdown you need. So again, raw water there. These are the figures roughly for what you would expect to see. So these are the figures you would be reducing. So raw water, depending on your area, non-hardness salts. So we could reduce this effectively down to this level. So blowdown losses, a third solution. So if you've got a pressurized deaeration on top of your tank, so your feed water tank. You can reduce the losses by adding feed water at higher temperature. Yeah, so your water feed is in here, you're adding steam, or so steam into the system and effectively heating it so that it drops down through. Minimizes corrosion, less chemicals required. Again, it's all reducing the costs by chemicals and fresh water that you need to introduce into your boiler. So it minimizes air on the system too. So air is a barrier to heat. You want as little air as possible in your system because it also air and condensate mix encourages erosion. So you want to limit the amount of air that's in there, and the deaerator is one way to do it. So storage calorifiers, many of you guys would have somewhere. You have a tank which is storing hot water. So it's popular types of calorifier and storage type, combines a shell and tube heat exchanger in the body of the storage vessel, and temperatures range usually between 60 and 80 degrees, 100 to 120 degrees when you're talking about medium temperature hot water and higher. So many of these systems you'll see, there's a typical tank, you have your control, you're coming in from your steam supply, you have your trap sets running through, and temperature control here. Most of the time this temperature control tends to be mechanical. So how do we reduce the use of that? So challenges we have with the calorifiers is the duty, the sizing, the footprint. It takes up valuable space in our workshops, in our factories. Storage and standing losses. So as this water is heated, it's slowly losing heat because it's radiating through the material. You have to maintain it. So and the manual handling of moving it into place and the equipment replacements. PED, so pressure equipment directive. So because this then becomes a pressure vessel, it needs to be tested, which includes insurance inspection costs. There's a risk of Legionella, so any standing water above below 65 degrees, I believe, can hold Legionella. So that's why we heat to above 65. You've got to control that water somehow, so you're consuming steam. Again, the fouling and the scaling you can get in the system, and there's no future proofing. So what we say with that is a calorifier, a heater, heating tank is what it is. There's no better improvement you can make on the design. You can improve its efficiency, but the design will always remain the same. So typical calorifiers. Thank you to South Africa for the image. So a solution, how can we reduce all that footprint? So one way would be to use a heat exchanger package. So it means that you can almost instantaneously heat water, so there's no need to store it. Has a smaller footprint, so that the area in your factories can be better utilized. Doesn't have any storage loss because there's no storage in there, so therefore you're not losing any radiant heat from a large volume of water. No manual handling, so that's more to do with the replacement of equipment because it's a package unit. There's no pressurized equipment directive, no PED, because there's no pressurized vessel. It doesn't need insurance costs. Zero risk to Legionella because again there's no standing water. Good temperature control because it's on the line. Minimal fouling because the square area of the unit is smaller, and it future-proofs because you can improve the equipment that's on it. So I know we show our easy heat unit there, but there is other heat exchanger units you can use. A heat exchanger is always going to be more effective than a calorifier because, again, like we said, it's instantaneous and the other reasons that are listed there. So pure example of those units sat into place instead of those tanks. Does anybody have any questions there?
We don't have any questions.
Okay, so we've only got a few slides left, which is good. We might actually be on time. So metering. So why would we meter? Again, goes back to the questions you guys were asking. You want to know how efficient your system is and where you can save energy. So steam flow, we could check the main header supply, the building supply, the process supply. Condensate, the process return, the building return, the feed tank return. And then on the feed tank itself, the water supply, boiler water supply to it. So again, we touched upon it earlier, where the best place to place meters are. I would suggest that these are probably the best places as a minimum. Of course, you can always add as many meters as you want, but if you're looking to check the whole system, these would be the places we would suggest. So M850, so B850 even, sorry. So we have a energy monitoring unit, which allows you to check the energy transfer efficiencies, the energy losses from your TDS and so on, steam flow rate. So monitoring systems are typical. So some figures here are boiler efficiency. So if you assume your boiler is running 85% efficient, but it's actually 70%, so you've got a difference of 15% there. Cost per hour, let's say it's $190 per hour. The actual value is, because of the difference between these two, is actually $217, giving you a $27 different. So the cost per year, as you can see, it's over normally just